Okay, let's start. Maybe it's okay. Okay, great. So far in this course, we have seen how to make an op-amp, and the op-amp, as we know, takes in the difference between two inputs, amplifies it, and gives a single-ended output like this, right? So such single-ended output op-amps are very commonly used in discrete components. So for example, let's say you will have a PCB on which you will mount or you will instantiate this op-amp as a discrete component, and the whole bunch of other components you will make connections on the board and form a system. So in these places, this op-amp is very common, but it turns out on chip when you are trying to realize this has some issues. Okay, and as I typically say, it is nice to have problems because only then as engineers you all have jobs. So it is good to have some problems. So let's see what are some problems that we might have with this, and what is the solution for them. So firstly, let us say we have a system that is formed like this, wherein we have multiple small blocks making a bigger system. So here each of them is not an op-amp as such, it is some circuit made using an op-amp, right? And the op-amp, as we know, has a single-ended output, so it all takes one wire for processing the signal. Okay, and as you know, each block will have its own ground and supply, and let's say all of these guys will have the same supply. So this is connected like this, and outside the chip you will go and connect it to a power supply like this. Okay. But this is far from reality, because if you think about it, what we are essentially doing is shorting these 2 points with a metal. Now a metal line is not a pure short, right? So what all does it have? It will have a resistance. What else? I mean, capacitance is formed between two metals. If I just have one metal line, it will have some inductance, right? So here I will have a series resistance and an inductance. Same is the case inside the chip also. So we will have small resistor and inductors whenever you make these connections. Of course, the outside this line will be so long, so this R and L will be much larger than the ones you have on chip. Okay, cool. So now let us say this block contains switching circuits, right? I mean, switching circuits can be any switch capacitor circuit or analog to digital converter, and the easy way for you to visualize it, you can think of it like a digital block. Okay, so it is basically working on a periodic clock like this. So now let us say you have a digital block made using CMOS logic gates. When will it consume power? Yeah, static power consumption is 0, and the CMOS logic will consume power only at the clock edges. So let us say it will draw some current like this, something. Let's say around the rising edge it is going to draw some current like this. So this current is going to be a spiky current like this, fine. Now of course this spiky current has to be provided by this path. Okay, so which means the VDD, your actual circuit sees, is not the actual VDD you are providing externally. It is this VDD minus the drop across this guy. Now if the resistance is small, this drop across the resistor might not be so much. But if you look at the drop across the inductor, what is the voltage across inductor in terms of its current? It's derivative of the current. So the current waveform is looking like this. So if I take the derivative, it's going to be really huge, right? So which means this guy will see a huge jumps in the supply. This is good or bad? Yeah, bad simply because I mean, which means that the transistor inside might easily go in and out of saturation, right? That's the simplest thing. So this is something that is not good. So let us see what could be one fix for this. So here, let me draw it here. The issues here, we have spiky current drawn in this path. So if you think in detail, the problem is arising here not because this block is consuming spiky current. That is something it can't change. That is the behavior of the block. So this is going to draw this spiky current. The problem is not this current is spiky current. What is the problem? Yeah, basically the spiky current is flowing through this path. So if you want to avoid this problem, what should you do? Inverts. Just inverts. See, I know that this is going to draw spiky current. I don't want the spiky current to come from here. So which means I should have some other path to provide that spiky current. That's all. So I should somehow introduce an additional path that is going to give in the spiky currents, right? And if I look at the frequency spectrum of this current, do you think it will have significant high frequency component or low frequency component? It's very high frequency. So this path here should provide a very low impedance at high frequencies compared to this branch. Only then the spiky currents will prefer this path. But at DC, what can you say about the current that should flow here? That should be 0, because at DC at least you want this guy to be short like this, right? So essentially you want to put something that is providing a very low impedance at high frequencies, very high impedance at low frequencies. What is it? Capacitor. So typically this is something you can do. You can go and put a capacitor right next to your circuit, and this is often called the supply bypass capacitor.
So those triangular blocks are consuming spiky currents.
Correct. Yeah. One or more of them can consume spiky currents. Okay. I mean, this should not be surprising, because if you think about it, if you have a very infinitely large capacitor charged to some voltage, how does it behave like? It behaves like a voltage source, right? I mean, infinite capacitor has infinite charge. An ideal voltage source can provide infinite charge. It's all one and the same. So the act of putting a capacitor here is like you going and putting a local voltage source next to your circuit, so that is providing the spiky currents required, right? Okay. I mean, you can also visualize it by looking at the impedance profile. So if I redraw the same scenario we have, I have the external battery, I have the parasitic R and L, and then I have the circuit here. So if I look at the impedance here and plot it versus frequency, how will it look like? Okay, at very low frequencies, what will be the impedance? It's only the resistor. So it's, let's say the resistor is small, so we'll have something like this. And as frequency increases, it will increase. So that is why now you see that at very high frequencies you have a large impedance, and that large impedance drops a large voltage when the current flows, and that is what is resulting in the huge jumps here. Fine. Now what we are proposing is, we are proposing to go and put a capacitor right next to your circuit. So if I plot the capacitor impedance, it looks something like this. So now the effective output impedance is the parallel combination of these two. So you have at low frequencies, you have this large value and a small value. Parallel of the two will be dominated by the small one. Similarly, at very high frequencies, this will dominate. In between, you will probably have something like this. So now you see that the moment you add a capacitor here, the impedance that was peaking at high frequencies has now reduced. And that is why even this jump will reduce. Now if you go and put a very, very large capacitor, you might maybe do something like this. And I'll use this color. If the capacitor is very large, the impedance of the capacitor will look like this, right? So now if you take the parallel combination, it will nicely look like this. So if you go and increase the capacitor here that you are using for bypass cap, the change in your supply will also keep reducing. Right? And in principle, if you want to eliminate it completely, you have to go and put an infinitely large capacitor. But of course, that is not practical. So you will try to have as large a capacitor as possible. And remember that this capacitor has to be placed just close to your supply of the circuit, right? You can't keep it outside the chip because then that will completely destroy the purpose. It has to be sitting right next to your supply so that it compensates the inductance you have. So yeah, but having a large capacitor is also not a practical solution because it's going to take up a lot of area. So in practice, you can put a limited cap. So which means this problem will not get eliminated completely, but you can reduce it to some extent. So the final supply you see here, that will be your actual VDD. On top of it, you will have small variations. Great. So now let's see if you have some small variations in your supply, how will the op-amp respond? And let's take our 5 transistor OTA as an example. I'll quickly sketch it. So now what we are saying is the supply here is going to be VDD. On top of it, we are going to have small variation. We are interested to see if any variation happens in the supply, how is it going to appear at the output? Okay, that's the goal. True. So now let's assume that we already put a large capacitor on chip, so the variation in the supply is small. Okay. So if the change in the signal is small, to find how much of this change appears at the output, what can I use?
Small signal.
I can use small signal because the assumption is this is a small signal. So it's a small signal analysis. You can find the short circuit GM R out and find it. That is one way. I'll give that as an exercise for you to do. But this guy is something that we have analyzed extensively. So we should be able to do something better, right? So okay, let me just short this. There is no input applied here right now. So yeah, instead of finding the short circuit GM and R out, can you suggest some other way in which I can analyze this quickly? Huh? Why half circuit can use? Yeah, see, if you recollect, this circuit is asymmetrical, but under what conditions we saw that this becomes symmetrical? If there is a common mode excitation, that is the gate to source voltages for the NMOS and the PMOS are same. Here, what can you say about the VGS of the two transistors? The two NMOS have the same VGS, same with the PMOS. So you can reduce it to a symmetric circuit. That's because these two potentials, they will be same. You can go and short them. So that will reduce a circuit like this. You'll have the 2 times the PMOS transistor here, 2 times the NMOS transistor, and the current source is there, that's going to be open in small signal, and here I'll only have the incremental change in the supply. So this is our output. So now tell me what will be small signal V out in terms of Vn. Why?
Current is 0.
Yeah, see, current is 0 here because this is open. Incremental current should be 0. And incremental current, I mean, there are multiple ways in which you can look at this. Incremental current is GM/VGS, right? So which means these two must be same. Other way to see is, see, here I have a voltage source, and that voltage source is dropping between this resistance and this entire resistance here. What is the resistance of this block? Infinite, it's open. So if it's an infinite resistance, everything is going to drop across it. So this will be equal to V. So which means that if I make any change to the supply here, that is directly going to couple to the output. Right? Is this good or bad? Bad, right? And there is a term to quantify this behavior, and that is called the power supply rejection ratio. Or PSRR. So the definition is this: it is the ratio of the gain you want from your circuit, that is the gain you want from your desired input to the output, to the gain you have from the power supply to the output. Okay. So what is the gain you want from your desired input to the output? What is the gain? Gm of the NMOS times the R out. So I'll just write it. The desired gain from your actual input to the output is this. So I'll call it AD, divided by the gain you have from the power supply to the output. And what is it in this case? I mean 1, right? V out by Vn, it's 1. Now ideally, how do I want this PSRR to be? Yeah, infinite, right? You don't want this gain. This has to be 0. So ideally you want this to tend to infinity, but of course in the circuit that we have seen, it is only finite, right? So this is one issue with the single-ended output op amp. That is, let me just maybe say this is the first issue. It is sensitive to any supply disturbances. Okay. Great. Now, one more issue we can have with this implementation is the following. So let us say you have the signal that you want to route from one block to the next block. So you will have a metal line like this, connecting the output of the first stage to the input of the next stage. So let's say this is some V1 of t, and let us say adjacent to this you also happen to route another signal, some V2 of t. Right? Now if you have two metal lines adjacent to this, what gets formed? The capacitance gets formed. So there is going to be some parasitic capacitance formed between these two. So ideally I expect only V1 of t, or let us say some k1 times V1 of t to appear here. But now what will be the signal I get here? I'll have a small fraction of V2 of t leaking to that side. Fine. So let's say that is some beta times V2 of t. So that is not great, because you see that this signal is kind of interfering with your actual signal. I mean,
is that called coupling?
you can call it as coupling, right? Interference coupling is also. Yeah, and not just that, if you look at the signal here also, that will also ideally you want it to be V2, but you will have some, I mean, as I say, I mean, it's not like only your neighbor should not dump their garbage in your house. You should also not dump your garbage in their house, right? It should be mutual. So this is another issue, that is this sensitive to any interfering signal, or I'll just say interference. I mean, so what can happen is, let us say here you are trying to pass a sensitive analog signal which is varying very slowly, right? I don't know, something like this. And here let us say you happen to route a clock like this. So the rising edges of the clock or the falling edges of the clock, they will basically get coupled to it. So we will have something like this, right? Great. So one more issue that can arise with the implementation is this. So let me actually go back to the power supply. It's similar to the issue with power supply. So let me erase this. Oops. Yes.
How did we transition from PSRR to talking about capacitive plates?
Okay. So I was the okay. The starting point was what could be some issues with the existing op-amp implementation that we know that takes in two inputs and gives one output. That's all. The possible issues we can have in this implementation of op-amp, which has one output, is what we have been looking at. One was the supply dependence, that is, any disturbance in the supply will couple to the output. And second, if you have a single-ended output like this, it is prone to interference. And the third is this. So here I have only shown the supply, but recollect that even the ground is common for everything. So you'll basically connect everything with one line. So which means even that line is not a short. You will have R and L in that path also. Right. So which means it should be clear, the ground the first block sees is definitely not the same the second block sees, because you will have again the switching currents flowing in this path, causing the ground also to jump. Right. So that is a big problem, because now the first block is generating a signal with respect to a ground VG1, but the signal that the second block processes is with respect to VG2, right? So the signal itself is getting corrupted in this process, so that completely corrupts your signal processing. Is that fine? So this is, I'll mark it as third. I'll just say sensitive to ground disturbances. Right. So let's see what could be a solution for all these. For that, let's start with the last problem of ground disturbance. So if we actually think about it,
So these problems are significant only if we have switching circuits.
correct, and typically that's what you'll have on chip, because you'll have some kind of digital DSP is going to be there,
Okay.
and analog to digital converter will be there, right? So it's not only an analog circuit. What we'll have is a mixed signal circuit, a combination of analog and digital. Yes, that's a good point. Yeah. So now if you think about why we have this problem, it's happening because the output here, let us say output of the first block, is defined as a potential difference between two lines. First line is local to this guy, and second line is the ground line, which is common to everyone, right? And since this ground line is common to everyone, everyone is going and dumping their garbage there and corrupting it, right? So if you were to be immune to this issue, what can you do? The issue is the output is defined as potential difference between two lines. One is a line local to this block that has no issues. The second line is common to all the blocks, and that is what is causing the issue. So if you were to work around the problem, what is the solution?
Introduce another line which is isolated from the.
Yeah, I mean, instead of having one local line, as he's suggesting, we can have two lines that are local to the block, right? And I'll say that the output is defined as the potential difference between those two lines, right? Basically the negative line, which was ground, which was common to all the blocks, I'll not have that as my reference. I'll have a local line within the block with respect to which the output will be defined. So now the second block will take it like this, process the signal, give out things like this, and so on. Okay. So now let us say if the ground changes for the first block, let us say there is a sudden jump in the grounds. So if the ground, I mean, remember ground is the reference to this circuit. If the reference to this circuit increases slightly, what can you say about the voltages here? They will also change by the same, right? I mean, the ground is 0, that's a reference. If the 0 is not 0, all the potentials in your circuit will change. So which means both these guys will change by the same amount. If you take the difference, it's okay. Okay. So that is the idea, and this is typically called differential signaling. The idea is simple. You have two lines running in every block. The output is defined as the potential difference between these two lines. Okay. So I'll call this as some VO of t. So the positive line I'll call it as VO plus of t. The negative I'll call it as VO minus of t.
There also we can have resistance and inductance for that line.
Yeah, but that is okay because there you will not have spiky currents, right? The spiky currents are drawn from the supply. Here you will not draw any currents. Okay. Okay. Great. And so now we know that this differential output is going to solve the issue with ground. So let's see if it is helping with the other two problems. So let's look at the interference issue. Let me just copy this. So now the output is not a single-ended output. I have VO plus of t. So here I'll just change the notations. So it is. So now I no longer have one line, I have two outputs. Okay, so let us say I route the minus line also like this. This VO m of t. If I make sure that I route the negative line in the same metal layer as this and I place it at the same distance as this, what can you say about the two coupling capacitors? They will be same. And this is something under your control. You are the one who is going to make these connections. You make sure that the positive and the negative lines are routed with the same metal layer and interfering signal are at the same distance. Okay.
So won't you try to route it like this, the middle line like this?
Which one?
The V2 of t perpendicular.
Yeah, that's actually a very good point. If you want to avoid interference, this is the best thing you should do, right? But sometimes let us say you can't avoid it. I mean, let's say you can't help it, and to get to this point, if you route two metal lines like this, that has the least capacitance, right? So as we pointed out, if you want to minimize interference, this is what you should do. Here again, you will not have zero interference, you will have something, right? So now if I look at the signal here, V2 is going to couple to here, the positive side, and similarly it is also going to couple to my negative side. So if I take the difference between the two, what happens? It's gone, right? So now if we look at what happens to the line V2, so here earlier I just had a fraction of the this signal getting added. Now what I'll have? I'll also have the same fraction of the other signal. So now if I don't want this to be changed, that is I want this to be equal to V2 of t. How will I choose VOP and VOM? I mean, if I want this to be equal to V2 of t, yeah. So that's what we typically do also. We choose so we know that V out of t was defined as the difference of these two, and on top of it you make sure that the two are negatives of each other. So which means this is going to be plus VO by 2, this is minus VO by 2, and usually of course we don't have negative voltages, so we add DC bias. I'll call it the output common mode. So this is the output common mode, that is the output DC bias that we are adding. Okay, great. So yeah, so this is the second issue. Let's look at what happens with power supply.
Sir,
Ah.
so if I have two metal lines for V2 up T, then this choice is not necessary, right?
Two metal lines meaning?
Two metal lines, just like we have VOP and VOM.
Okay,
We have
if
two metal lines for V2.
yeah, so typically, I mean, in, let us say if you have a case like this where I showed, right? So let us say this is V2 is a clock, let us say that is a single-ended output, isn't it? So in that case, if you do it like this, the clock is going to couple the same way to the two signals. So if you take the difference, it goes away. Great. So let's look at the power supply issue. So now I know that my signal is like this, and one trivial way to generate this differential output is this: you take one block that takes in plus Vi by 2, you have an identical copy of this block, and what should I give here? Minus Vi by 2. This is one trivial way in which we can get this. So let's take this as an example and see what happens to the supply. So once again, both of them is going to share the supply, and if the supply has a change Vn of t, let us say for the first block, some alpha times Vn of t appears at the output. Now the same supply is given to the second block also, and this is the same identical block as this. So what will happen here? Plus same alpha times Vn of t. Fine. It's an identical block. So if for the first block, alpha times the supply appears at the output, even for the second block the same is going to happen. So once again, if I take the difference between the two, they're okay. Right? So that is why in practice all analog and mixed signal circuits on chip, they are realized like this as a differential circuit. So you'll have things working like this. The only place where you will find single-ended output implementations are where you want to interface to the real world. For example, if you want to sense a signal from a sensor, typically it might give a single-ended output. So if let us say this is the boundary of your chip, here you will have some circuit converting the single-ended to a differential, and everything is processed in a differential manner. And let us say finally you want to drive it to another transducer or some speaker, that will require a single-ended output. So that is where you do this. But otherwise everything on chip will be differential because of all these reasons. Cool. So now let me actually extend this. We'll erase this. Great. So again, not needed this. So as we saw, this is one way in which you can have this differential implementation. Okay, but if you think about what this is doing, if let us say this is a gain A, okay, and we implement this gain using a common source. To make a differential, what we are suggesting is I take an identical copy, feed minus Vi by 2, right, and then call the difference between these two voltages as your final differential output, right. Although this works, this is not commonly done, and this has some issue. And what is that?
Common mode rejection.
Yeah, if you think about it, this does not have a common mode rejection, right, because if this is a gain A, the output here will be A times Vi by 2. This will be minus A times Vi by 2. On top of it, if we have a small common mode added, what will be the output here? Huh?
A times VIC.
I mean, the total signal here is Vi by 2 plus VIC. It's going to amplify it by a factor A. So we'll have A times VIC. Here also we'll have it. Now, of course, if you take the difference between the two, VIC goes away, right? But the issue is this, right? If, let us say, the signal you are trying to sense is really small, and the common mode signal that gets added is much larger, that larger signal will get amplified, and that might saturate your complete system, right? And that is something you don't want. And that is happening because this system does not differentiate differential and common mode signals, right? In other words, this has a poor common mode rejection ratio. Okay. And this implementation is called pseudo-differential implementation. Let me just write it. It is differential, but it is not truly differential in the sense that it is also responding to common mode signals. Okay.
But eventually we are subtracting the common mode signals.
Yeah, but that is, I mean, you are subtracting by looking the difference between these two signals. But this signal itself will contain the common mode. And what I am saying is, if the common mode is typically larger than Vi, A times VIC can be very large. This can saturate to supply. Then you are losing out any information. Okay. So to improve the common mode rejection ratio, how do you suggest we change the circuit? You guys know this, right? How do you get a common mode rejection here?
Current source.
Yeah, if you recollect, we had a tail current source. Like this. So now you take the output as difference between the two. So this circuit, as you know, does not respond to any common mode changes, and that is why this is called a fully differential or a truly differential op amp. So this will have all the advantages of your differential signaling, that is, it is immune to, right? It is immune to supply changes. It is immune to any disturbances in the ground. Also to interference. And on top of it, it has a good common mode rejection ratio. Right? So any kind of common mode disturbances, this guy is immune to. Okay. So again, in addition to all these things, another nice thing about the circuit is that if you look at the circuit, how does it look like? I mean, visually, how does it look? Huh? No, I mean, not technical. If you look at it visually, how does it look? Symmetrical, right? So now you can nicely analyze using all your half circuit symmetric concepts. So even analyzing it is going to be much more easier. Okay. So let me just copy. We have done this before. I'll do it once again for completeness. So if, let us say, I give a differential signal, what is this potential? Ground, 0. So the differential half circuit, the differential mode half circuit then is this. I can take only one half of the circuit and analyze. Here I'll have VID by 2, and let us say this is VOP. So what is VOP? Minus, let's say minus GM times R. I'll ignore the output resistance to VID by 2. So what do you think VOM will be? It's a negative of it. So it will be plus GMR VID by 2. Fine. And because the negative half circuit is the same, just that here I will have minus VID instead. That's all. So the final output is going to be what? Minus GMR times VID. So this is your differential mode gain. Similarly, if I apply a common mode signal, I can draw the common mode half circuit. And how is that going to look like? In the common mode, these two potentials are same, so I can short it, so things just come in parallel. So this is R by 2, this is VIC, this is 2 times the transistor M, and you have the current source. So what is VO here? 0. So the common mode response is 0. Great.